Welcome to another episode of TutorTube. Today we'll be talking about related rates. So example 1 here, the top of a ladder slides down a vertical wall at a rate of 0.25 meters a second. At the moment when the bottom of the ladder is 5 meters from the wall, it slides away from the wall at a rate of 0.15 meters a second. How long is the ladder? So this here is the wall, and this here is the ladder. And notice that this is a right triangle, and what do we know about right triangles? They're governed by this equation, by the Pythagorean theorem. And so what do we know about related rates? We know we need to take the derivative of whatever equation we have. So this becomes 2a times a prime plus 2b times b prime equals 2c times c prime. And notice that you can divide everything by 2, and you're left with a times a prime plus b times b prime equals c times c prime. So all that's left to do now is to assign variables. So we'll call this a and we'll call this b. And if we get a and b, we can also get a prime and b prime. And it's pretty much plugging and chugging. So a, 5 meters away from the wall at a rate of 0.15. And b, sliding down at a rate of 0.25. So b prime would be equal to negative 0.25 since it's sliding down. So that leaves us with c and c prime, but we know that c prime represents a rate at which the ladder changes length, since this is the ladder, and we know that the ladder never changes length, so c prime would be 0. So plugging and chugging would give us that formula, and since we know c prime is 0, we can further simplify this to be 0.75 minus 0.25b, just by simplifying that expression. And so we solve for b and get the actual value of b, how long the ladder is, or how long the wall is, and from there we get 3. The wall is 3 meters long. So how does that help us find the length of the ladder? Well, we go back to our Pythagorean theorem, and since we have a given us 5 meters and we have b given us 3 meters, we get 5 squared plus 3 squared equals c squared, and utilize algebra to solve for c, and we get the square root of 34 for c, which is about 5.8 meters. So the ladder is 5.8 meters long. So the third example here, I'll be using this slide to illustrate what's going on, and then I'll be using the second slide to actually compute the problem. So water is leaking out of a tank that is shaped like an inverted circular cone at a rate of 10,000 centimeters a minute. At the same time, water is being pumped into the tank at a constant rate. The base diameter of this tank is 4 meters and the height is 8 meters. If the water is rising at a rate of 15 centimeters a minute when it is 2 meters deep, find the rate at which the water level is rising. The water level is being pumped into the tank. So this is a differential equation problem, but if we solve for one of these variables, we can actually make it a related rates problem. So that's what we'll do. But the first thing we want to do is make sure everything is in the same units. So we want to change everything from meters to centimeters because we actually want to find a rate. So the rate that's given, the units of the rate that's given is in centimeters. So we want to change everything to centimeters. So the base and the height, the diameter of the base is 400 centimeters. Using dimensional analysis, we multiply everything times 100, and that means that the radius divided by 2 would be 200 centimeters. We want radius because that's what we use in our equation. And then the height of the entire cone itself is 800 centimeters. So let's move on to the next slide and see what else we need to compute this problem. So the question asks us to figure out the rate at which the water is being pumped into the tank. So how we express that is by using the formula for volume change, which is V prime. And we'll let that be equal to, say, P prime, which is what we want to solve for, the rate at which it's being pumped into the tank, P for pumped, minus the 10,000 centimeters cubed that is leaking out of the tank. So that should give us our V prime. Next, we need to remember the radius is 200 centimeters, and the height is 800 centimeters of the entire tank itself. So using those two pieces of information, we know that R will be a quarter of the height. So how is that helpful? Well, we'll use that to plug and chug into our volume equation. Remember 1/3 pi r squared h. So it becomes 1/3 pi times 1/4 h squared times h will give us our volume. Not our V prime, but our volume. So if we have our V, though, we can get our V prime. So then the question is asked, why exactly do we plug in for h instead of r? Well, since we have h prime as 15 centimeters a minute, we need to get everything in terms of h in order to plug h prime when we take our derivative. So first of all, we need to simplify the V expression as pi over 48 h cubed. And then we need to take the derivative in order to bring about h prime. So if we take the derivative of pi over 48 h cubed, we get 3 pi over 48 h squared times h prime, which is simplified to pi over 16 h squared times h prime. Now that we have that, now that we have V prime, we can substitute V prime in our V prime equals P prime minus 10,000 centimeters cubed equation up top here. So once we do that, we also need to plug in the rate at which the water level is rising and the rate at which and how deep it is when that rate is rising. So how deep it is 200 centimeters, and it's going 15 centimeters a minute when it's 200 centimeters deep. So that is equivalent to P prime minus 10,000, and then all we need to do now is solve for P prime. And once we do that, we get 37,500 pi, which represents this here, plus 10,000 when we move the 10,000 over. So P prime is equal to 127,810 centimeters cubed per minute. So you are situated 16 kilometers from the launching pad of a rocket. Suppose the rocket travels vertically at 1,200 kilometers an hour. Find the rate at which the angle between the telescope and the ground is increasing 3 minutes or 0.05 hours after liftoff. Give your answers in radians per hour, accurate to 2 decimal places. So the rocket is traveling 1,200 kilometers per hour straight up. And this problem, we're not worrying about any drag or any air resistance. We're going to keep it as simple as possible, kilometers an hour, and situated 16 kilometers away from the rocket. And we want to figure out this angle theta, or rather the angle, the rate at which the angle theta between the telescope and the ground, which we'll say the telescope is right here, is increasing. So how will we do that? Well, notice again that this is a right triangle, but instead of Pythagorean theorem, we will be using trig, specifically the tangent function y over x. So we know it's a right triangle, so y in this case will be 1,200 and x will be 16, but remember that these are different units. This is where units come into play. So when we do that division, we get 1,200 over 16, and the kilometers cancel. So we have h on the denominator, and 1,200 over 16 simplifies to 75. So we get 75 divided by h. So now we need to remember that tangent theta is supposed to be unitless. So the hours are supposed to cancel. So how do we make hours cancel? Well, we'll multiply it by a variable that we make up, t hours. T is not a unit. T is in hours, so hours cancels out with the hours on the denominator, and we get cancellation, which is what we want. So we get the expression tangent theta equals 75t. So let's remember exactly what we need to solve for. We need to solve for theta prime. So now that we have an expression, and using our problem, we know that 3 minutes after liftoff, we can get the actual angle at which the telescope and the ground after a certain point in time actually is. So we're going to get the actual theta value, which will be used to help us calculate theta prime. So the first thing to do is get theta. And how do we get theta? Well, tangent theta is equal to 75t. T is 0.05 hours or 3 minutes given by the problem. So 75 times 0.05, well, that's 15 over 4. So tangent theta equals 15 over 4. How do we get theta? We use tangent inverse. Tangent inverse of 15 over 4 is equal to theta. So in the problem, we want theta. To solve the problem, we want theta prime. And we've gotten theta to help us. So now let's use the expression that we found, tangent theta equals 75t, and let's take the derivative of that. Let's use related rates. So that becomes secant squared theta times theta prime equals 75 once we take the derivative of the left side and the right side. And this is coming from this equation here that we found already. So remember that secant squared is really 1 over cosine theta, the whole quantity squared, times theta prime equals 75. So we want to solve for theta prime, remember? So we need to multiply both sides by cosine theta squared. And I've written it this way to signify exactly how you'll plug it into the calculator. And we have an expression for theta. So we have an expression for theta prime. And we have theta as well. So now we plug in all the variables that we have, theta given as that. And this is exactly what you'll plug into the calculator. You could simplify theta to be about 1.31, but you want to be as exact as possible. So I would advise plugging in the tangent inverse, plugging in that whole thing into the calculator, just as it's expressed there. And once you do that, you'll get theta prime is equal to 4.98, rounding off to 2 decimal places. And that's in radians per hour. Thank you for watching another edition of TutorTube. Check out what else the Learning Center has to offer in the links below.